Well, this is the third of our lectures, and we're going to start talking about data types, the different syntax in Java that you use to represent data. Constants, variables. You know, Java is a language where you have to declare your variables up front. We'll get into some of the operators and some other reserved words, like the math object, and some type conversion, things that you need to be aware of as you're manipulating your data with the different expressions and stuff that we create in here. So once again, just reviewing, I say this over and over again, but I want to just drill it into you, like the process that we do when we start working. First, this is the way I recommend doing it, is to go create your GitHub repository first. You don't have to. You can just start working locally in a folder, just creating a project or files or whatever you want to create locally, and then you can create the GitHub repository and add it later. But I find some of the commands that you have to look up hard to remember and awkward to use, the parameters and things that go along with them. You have to know more about Git and GitHub to wire that up correctly after the fact. But if you just start from the beginning and create your GitHub repository and then clone it locally, the clone process is easy to use and straightforward, and it pulls down all the settings that it needs to wire what's local with what's remote in GitHub. It remembers where it came from, kind of thing. If you do it after the fact, you've got a folder full of files, you have to first turn that into a repository, and then it complains that, oh, there's already files in this folder, so you can't create a repository. Well, you can, it just takes extra stuff. And then you have to say, oh, and by the way, be aware that I have this remote repository, so you have to use commands that modify the Git repository settings locally to make note of where the remote lives. It's just a whole bunch of extra steps and it's awkward. If you just start and create a GitHub repository first and clone it, it's one step and then it's ready to go. You add files, you edit files, you commit them, you push them. It's all much more straightforward, and you're running on the well-trodden paths of Git commands as opposed to coming up with the obscure stuff to fix it after the fact. But so it's not mandatory, but I prefer it because I'm lazy. I prefer to use as few commands as possible and to remember as few parameters and things as possible because I know I'm going to have to look them up every time I use them. Okay, so we create the GitHub repository, we clone it locally, and then IntelliJ is pretty cool because if you're using IntelliJ, one of the options that it has right here at the beginning, you can either open a folder that has a repository in it, or you can just start off with the clone button, and all you have to give it is the address of your remote GitHub repository, and it will do the rest of the commands and stuff for you. It's one of those things that we like about IDEs, integrated development environments, is it knows all the commands and it will wire things up so that it remains happy, as opposed to us having to do it or to debug and diagnose what we did wrong later. So that's another option. Just create your GitHub repository remotely, run IntelliJ, and use the clone repository button here, and that'll take care of everything for you. Yeah, so then you write your code. Once in a while you hit save, you commit your code. You know, oh, I just finished this cool feature. I'm going to do a commit right now. That way I can always come back to this point later if I screw something up. You work a little bit and add another feature. You commit it locally, create a checkpoint where you can go back to. You do that however many times you want to. And then when you're comfortable, okay, I think I'm at a stopping point for the day, you can push that to your remote repository. And then just remember in here in particular, you don't have to do this at home, but here in particular in class, just shut down and restart the computer at the end of the class. Because you don't want somebody else to come in after you and open up IntelliJ and have all your GitHub settings there, and they can start cloning your projects and committing to them. So that stuff would be persistent until you restart the computer. Okay, so jumping into this topic, so basically just a high-level overview of what we're going to try to go through. In any programming language, you're going to have different data types. The two big groups are numeric and character data. And Boolean is a third one. But you could actually argue that Boolean is just a flavor of a numeric data type. So it's essentially just numeric data and character data. Within numeric, we have integer data, and we have data that's represented to have a decimal point in it, fractional values. And then again, Boolean, which is true, false. But if you think of Boolean values as 1 and 0, it's just another number. Yeah. There are, we can get into considering our memory as a collection of bits. So a byte would be a collection of 8 individual bits. There's syntax to handle that. You can consider your variables or your data types as collections of bytes. So if we're talking about an integer, we're typically talking about 4 bytes of data. So 32 ones and zeros stacked on top of each other. And then we get off into the more exotic stuff, arrays, collections, stacks, heaps, all those kind of things. And then we've got the custom objects, the library classes and objects that are already provided for us by the development environment, or the ones that we create ourselves. Like if we're going to create a customer object, or a person object, or an animal object, then we would be creating that from scratch and setting the properties and the methods that govern the behavior of that object ourselves. So that would be our custom objects. So here's a quick rundown of the different data types. I would consider, even though you see char down here at the bottom, again, char can be thought of as just 2 bytes of memory. And in some, especially like in C++ and languages like that, there might be scenarios where you're taking a piece of memory that has non-ASCII character data in it, and we're just going to still use char to refer to that, just because we know how the operator we're about to use is going to treat that, and it's appropriate for what we want to do to that memory. These are some obscure things I'm referring to, but I want to throw them out there for completeness, just so that you get the full picture on a slide like this. So as I said, byte is just 1 byte of memory. If you're using that in a numerical context, as you can see, we're going to be able to store values from -128 to 127. Now, why is it not -128 to 128? Doesn't that seem a little weird? So why is that? Whatever you're thinking, it's probably right. Nobody?
Because it comes from 0, so technically to go to 10 you would start at 9, like 0 to 9 would be 10.
Yeah.
So in this case it would be the same thing.
Exactly. So we could think of it as 128 negative values and 128 positive values. We're just abusing 0 there and considering it in the group of the positive numbers. But yet we essentially have 128 on each side of the line. Yeah. And in the end, we've only got 8 ones and zeros. So if you do the math and you add up the combination of all combinations of a collection of zeros and ones, 8 of them, we only have 256 values. So we have to draw the line somewhere. I guess we could have gone -127 to 128 by convention, but There's other math reasons, like base 2 numbering system is what we use for representing numbers as combinations of bits. And so in base 2, 0 is lumped in with the positive numbers. Okay, short is the same treatment, but it's 2 bytes instead of 1 byte, so the number of combinations goes up, 32K to negative 32K. Int, same thing, but now it's 4 bytes, so we get a lot more values. And for most of my career, a 4-byte integer was pretty much the norm, the convention, and that was based on the fact that the processors were 32-bit processors. You know, the Intel Pentium, and that era of CPUs had 32-bit, 4-byte words, is what they would call them. And so what that would tell you is that that processor would be natively able to do arithmetic with 4-byte values. Another way to think of it is the CPU's registers. It has a set of registers as its scratch pad where it's doing all of the moving and shuffling data from long-term storage back to memory and back and forth. That the registers would be 4-byte, 32-bit registers. So that's how the processor would do natively. Back then, processors might have a problem with floating point arithmetic. Like the pre-Pentium processors were very, very slow with floating point. So often we as programmers, we would try to come up with techniques for managing our numeric data as integers and save the fractional values and those calculations for things where we didn't mind if it took a little bit longer. I mean, it was orders of magnitude. If you're doing integer math versus floating point math, your program would be lots slower. But then the processors got more and more complex, and Intel and AMD, the processor manufacturers, they started building the circuitry in the CPU to basically do fast floating point arithmetic right there in the processor. And so that basically leveled the playing field where it became just as fast or, comparably fast to do floating point arithmetic as integer arithmetic. You think I'm getting into the weeds on this kind of stuff, but we as programmers need to be aware of that. If you're just sitting there writing something in a higher level language, like Java, C#, C++, and you're writing the same algorithm as the person sitting next to you, and you're doing floating point math and they're doing integer math, theirs is going to blow yours away. So you need to be aware of the behavior of the CPU, what it's good at and what it's not. A long time ago, back in the olden days, again, there was a guy named Michael Abrash that he was an engineer. I think he worked at id Software, the people that made Doom. He worked at Microsoft for a number of years. Did some pretty seminal work in the area of taking what he knew about the processors and making sure that the way math libraries were written were as fast and efficient as possible, and that carried into games. Some of the reasons why we had better video games back then, like Doom, Quake, some of these things, is because these really smart guys were just getting every ounce of power out of those CPUs at the time that were relatively primitive in today's standards. But that guy, Michael Abrash, he wrote this book that was about this thick, I kid you not. It was called The Graphics Programming Black Book. You can probably look it up on Amazon still. It's probably dated now. If he had a new edition of it, it would probably be amazing. I don't know, maybe it'd be that thick now, I don't know. But it was interesting reading that book because he would go through each of the different generations, like the 386 processor, the 486 processor, the Pentium processor, and he would talk about why it was fast at certain things and slower at other things. And it was funny how what you would explicitly have to do to get the speed out of your program in a 386 You would absolutely not want to do that with a 486 because it would make your program slower. And then you didn't even have to think of it at all when you went to the Pentium because they redid the architecture and made it where, oh yeah, that's not even an issue, we don't even care about that anymore. But all these different features of the processor, they kept going back and forth. So you really had to stay up with what was going on with processors to know exactly how to gear your algorithms if you were targeting those platforms to get the most out of them. Sometimes you might have different code. You might say, oh, here's the version of this program that's optimized for a 486, or here's the version that's optimized for a Pentium, or things like that. But it was definitely a thing. And I'm sure, that's one of the things that Intel and AMD do to kind of one-up each other. It kind of progressed away from just the raw CPU features over into the GPU features of graphics when we started being able to store collections of triangles or polygons in the graphics card and have it do matrix arithmetic across a whole bunch of 3D points to animate pieces of data in 3D space for us. Yeah, it just got even crazier. And now with shading and texturing surfaces, it has gone beyond my ability as a non-gamer programmer on a daily basis to keep up with the state of the art in there. So if you're going to do game programming now, you probably ought to go take a couple of classes specifically targeted towards how to do high performance game programming nowadays because it's gotten so complicated. But okay, we'll put a pin in that because right now we just want to know in Java how to do math and be able to store what we need to. So when you look at a long 8 bytes, we get to a certain point there where I forget where the line is, but that number of values that we can store with a long, we may be getting close to like what they theorize as the number of molecules in the known universe kind of thing. So if you're trying to count the number of clicks on a web page, yeah, you probably don't need a long for that. The only reason why we use a long for that is if you knew that the processor that you were using was going to process it faster if you natively used a long, so then why not? So, but the reason why we even talk about these is because in general you want to try to pick the right tool for the job. Whatever variable you're about to declare, pick something close to the right data type for the task at hand. Having said that, that is the reason why we talk about this. But for handling numeric data, there's almost no reason why you would ever pick anything other than an integer, because it will store the reasonable range of values that we encounter, and the processor will handle it natively as fast as you need it to. So byte and short are there, but you probably never need to use them. Char. So the difference between char and short. So there is the notion of signed versus unsigned data here. Now I copied this straight from reference material, so I'm not inclined to doubt it. But if I was looking at this and thinking that we were talking about C++ here, I would doubt some of these descriptions. Like a byte in C# and C++ would be unsigned data. There would be no negative numbers. So we would store the values from 0 to 255, and you would not store a negative number in a byte. That's what a char would be for. A char would be a signed data type. So that would be the difference between some of this stuff. But it's Java, it's a higher level language than C++, so fine, if that's what the book says that the data types are, I'm not going to doubt it. But don't be surprised if you go to some other language. I'm guessing C# is going to map pretty closely to this, but C++ and C are going to have different things that you'll have to look up. And that'll be the biggest difference, is the signed versus unsigned aspect of it. So what happens if you take an unsigned byte in C++ and you try to assign a negative number to it? And we'll get to some of that conversion stuff here in a little bit, but essentially the compiler just says, okay, well, -1 representative of the positive number would be this, so I'm just going to copy the positive version of that into memory. But like I said, we'll get into that. I don't want to completely cause you guys to check out due to the obscurity of these facts that I'm throwing out there. I'm just trying to give you a flavor for what we're talking about here and what you have to realize if you're going to be programming. Yeah, so a float, does anybody know how in 4 bytes we represent it says a 6 to 7 decimal value in 4 bytes, as opposed to an int, which is -2 billion to 2 billion? Where do we get that switch over? Has anybody ever come across or looked up what the data storage format of a float is in memory? Well, they have, if you just Google it, float and double are the same again, but they're just different number of bytes. They have part of the bits inside there are dedicated to the whole value, and part of the bits represent what's behind the decimal. It's like 2 different numbers. Okay, and then they have another third number that says how many digits, where the decimal place is, if I remember right. But it's not magic, that's just how somebody defined it, and so that's how the compiler and the CPU, used to be the compiler, now that's how the circuitry inside the CPU treat those 4 bytes or 8 bytes, is we all agreed on what the rules were for representing a floating point value in bytes, and that's what it does. Boolean is pretty simple, 1 bit, but we don't, like I said a minute ago, we don't really store things natively, like in the CPU's registers. If the register is 4 bytes long, and the CPU says, oh, go get this Boolean value from the hard drive and load it into memory into a register, well, I still have 32 bits there, even though true false only is a 0 or a 1. So what does it do with the other 31 bits if you're processing a Boolean value? Well, what would you do with them? You only really care about the 1 bit, so you essentially just ignore the rest of them. Right? Now, it's a little bit different than that because, like if I put the value 27 into a register, clearly that's not a 0 or a 1, but the rules of the compiler says to treat anything that's a 0 value as false and anything that's not 0 as true. So that's your rule there. No matter how many bits you're using, you're occupying, if it's 0, all zeros, it's false. If any of the bits are 1, it's true. But logically, we can only hold 2 values, true and false. Any other questions there? Anybody still awake? Okay. I know it's a lot of, anytime you're going over reference material, it's a little dry and hard to get through. But, we kind of got to cover this stuff at least once. You have to have at least a record of me saying it once or seeing it in the textbook once so you know where to go back and refer to it. Okay, so in Java, like I said, variables have to be declared before you can use them. They actually have another state. So you can declare a variable, but you haven't set it to a value yet. So we're going to call that uninitialized data. You've said, I need this many bits or bytes for this value, but you haven't told the program what value to put in there, what to consider it. So the compiler is going to keep track of that kind of stuff, and it's going to say, if you try to use it like you're trying to print the value of that variable before you set it to anything, it's going to complain about that. It usually catches that kind of stuff in the compiler. If it doesn't, then when you get to runtime, you're going to have some logical errors there. So we declare it and we initialize it, then we can use it for other stuff. So the initialization of a variable, often you'll just see people set it to 0, or you'll set a string to double quotes, empty string. Sometimes, depending on what you're doing in your program, the fact that it's uninitialized may be a valid state. And there's a way that you can ask, is my variable set to anything yet, or is it set to nothing? So sometimes in some languages and some situations you might want to query that state. But typically, the happy path, 99% of the time in Java, you're going to declare a variable and initialize it to a 0 or something, whatever you want it to be, prior to the code where you're going to use it. So this applies to these data types: string, int, float, char, and boolean. Any of those, you're going to have to declare it and set it to a value before you use it. So, I don't want to draw this out too long and have another 2-hour-long lecture, but, we can demonstrate any of this stuff as we go. There's an example of obviously declaring and initializing an integer variable. So do you remember integer, how many bytes is that? 2, 7, 12. Come on, stick with me. How many bytes is an integer? 32 bits. Come on, help me out.
Was it 8? 4.
4 bytes. Yeah, just try to remember native register size is 32 bits. So lots of times by default, without thinking about the problem any further, we just automatically pick an int. Because it's 4 bytes, 32 bits, register size, word size, whatever you want to call it. Okay, so there's things in Java called constants, and this is how you declare and initialize one of those. The difference, you can think of these in most situations syntactically like a variable. We're going to give a name, we're going to put an entry in the name table. In this case, it's pi over 180. It's a valid variable name. You have to use valid variable naming schemes for constants. We're going to use the final keyword. We're going to use a data type. So it tells it how many bytes. So double, I won't do this to you again, but double is 8 bytes. We have a value over here that's a decimal value, has lots of decimal positions. This wouldn't work as well for a float though, would it? Because I got way too many digits after the decimal for a float to handle, right? If I tried to initialize that, it would probably truncate it somewhere around 6 or 7. Nobody really said anything about that, but that seems very imprecise, doesn't it? Sufficient for storing 6 to 7 decimal digits. Doesn't that seem a little out of the ordinary for a reference statement about a data type for a programming language? Well, which is it, 6 or 7, right? Well, that's because the values, the range of values, like the -128 to 127, if you actually go look up more about the floating point definition, the range of values, it stops. It can support some of these 7-digit fractions, but not all of them. So I don't know where it is. If you get up to 3, it's okay. If you get to 4, no, that's too high, and it truncates it there. I don't remember exactly where the limit is, but I'll leave that to you guys to be able to Google. But that's the reason why it says 6 to 7. There's some 7 decimal digits that it can store, and others that it can't do that, and it truncates them. So just be aware of that's what we're talking about here. But with a double, we got a whole bunch more digits. So that's your clue here. Oh, I've got a lot of digits, so I probably should use a double instead. Okay, so the basic characteristic of a constant is it's a value that we want to be set for the entire scope of our program. Anytime somebody refers to this abstract notion of a value, we want it to be the same all the time. We don't want some line of code to come along and say, oh, well, I think it should be 0.018. No, we always want it to be this value, and we're going to set that constant for the whole program. So we mark it as final, and that tells the compiler, if you ever see an assignment statement where somebody's trying to write to the bytes that we define, these 8 bytes for this value, don't let them do it. Give them a syntax error saying, no, sorry, you can't assign a value to this constant. You'll get some compiler message like that. So it's useful in those kind of scenarios where you have some kind of a value that you, for your program, considers important and you want to use it. You know, if you're doing some kind of a geometrical type thing and you just need something like that. For me, the convention, like I said, the name just has to follow variable naming rules, but my convention is that I make them all capitals. That way, if I'm reading my code later, I can say, oh, this what looks like it's used in the context of a variable name, but it's on all capitals. That must be a constant. I don't have to trial and error or guess or remember. I can just discern and infer from the naming convention of the variable that I defined it as a final. It's a reminder to myself. But why use these at all? Why not just type the 0.01745 blah, 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 blah every time that I want to use it? I could copy and paste. You know, I've got a really good copy and paste feature in my editor, so I could just copy it all over the place. There's a couple of basic reasons for that. One is sometimes you type those values wrong. Sometimes you look it up and you think, ooh, I entered that wrong, I need to change it. And you don't want to have to search across your entire source code base to find all the places where you use that value. So you use the symbolic version. That way you can go to one place where that value is defined and change it there. And then recompile and everything takes it. And then the justification for doing this at all, why go to the trouble, is again, it goes back to the compiler and the processor. If you give hints to the compiler about how you intend to use this, then it can sometimes optimize and make your code just a little bit faster in some scenarios. And, you know, modern CPUs, again, it's probably a lot more important a long time ago, but, you know, it's just the way we do things and just understanding how your processor works and writing the most efficient code that you can while you can. You know, I've had this guy over the last couple of days working on the electronics on my boat, and you know, all you got to do is plug the wire in here, plug the wire in there, and the lights come on, right? But this guy was more like an artist, and he ran the wires exactly where he wanted them to go. Oh, it's not long enough. Instead of just stretching it, he would just splice an extra piece of wire on there so that it went exactly where he needed it to. And he put zip ties around everything and made it look nice so that the next person that comes and has to work on the boat says, oh, look how nice and organized, and they can trace the wires exactly where they start and where they finish. He's used good trade practices. And for us as programmers, doing things like that is good trade practice. It shows that you are taking care and more of a professional with the way you produce your code, instead of just, well, yeah, I ran it and it worked once, so I guess I'm done. Move on. The last thing I want to point out about this is that you know, we have this math class, not something some other teacher teaches down the hall, but an object, a a Java class called math that's part of the libraries that we're given and we have access to for our Java programs when we write them. And that has a bunch of these constants defined in there. So math.pi, you don't have to go look up what, 3.14159 and all the digits. Somebody has already done that and put them in and called it math.pi. And math.e is the same thing for the e constant. And there's other constants, you can go look those up, the other constants that they have there. It's kind of interesting. I mean, it's just good to know that they're there instead of reinventing the wheel. Not like, if you had your own pi constant in your program, you're not wrong. It's not like pi changes, but it's just unnecessary. Just include the math library in your project and reference what's already there so you don't have to do it yourself, because that's what everybody else is going to do. Okay, the next thing is literals. Okay, so when I say literal, I literally mean this value. So when I say the value 101, it's the number 101 to us humans. One more than 100. We've got other English ways of representing these values, but I literally mean that value. And so in the computer programmese, I will type 101 to refer to the literal value 101. So that's why we call them literals. I literally mean that value. It can't change. You can't change the definition of 101 to be 17 or 112 or anything like that. No, anytime you type 101, you're always going to mean that literal value. But it's useful because I can say int count, declare a variable and initialize it to this literal value 101. That's the way we use literals. And there's a whole bunch of other ways that we can do those. As you can see on this slide, if you start your literal with a 0 character, I don't mean the number 34. I mean octal 34, which is actually to us humans decimal 28. Why would you ever do that other than to freak people out, right? Well, in certain scenarios, you're dealing with octal values, and it's easier for you to represent your algorithm by referring to the octal literals. I don't know why you would do that or when, but it works that way and you can do it. The reason why octal is a special numbering method is because whereas decimal is a little awkward because we don't have a fixed number of bits that can represent the values 0 through 9. It's a little more than one even number of bits, right? It's like 4 bits, but that's actually too many. But 3 bits exactly holds 8 values, 0 through 7. So that's an octal numbering system. If you're counting in bits, imagine instead of us having 2 hands with 10 fingers on each hand, imagine that you're an alien that has 3 hands and 1 finger on each hand that you can hold up or not. I have to be careful which finger I hold up there, I'll get myself in trouble, right? But if you're an alien and you've got 3 fingers, then you might count in octal. Okay? That's why we call it out, and that's why our programming language natively supports octal, is because it knows how. Same with hexadecimal. If we talk about a 4-bit numbering system, the numbers 0 through 15 fit evenly into 4 bits, or a half of a byte, right? And so you'll often see us in programming refer to hexadecimal numbering because of that. Decimal, like I said, is kind of in between octal and hexadecimal, and it doesn't fit nicely. So every time we say something like 101, the compiler has to do the math for us and say, oh, how many bits that's going to take to represent that value, or convert it up to a higher number of bits data type for us to hold that value for us. So it's doing the heavy lifting so that it can refer to us poor humans in our decimal native language. But octal and hexadecimal are native for the computer. Bits, I guess we can throw in there too. Oh, and before I go on, so if you want to define a hexadecimal literal, you just start it with 0x. And that tells the compiler what follows is going to be hexadecimal literal values. And notice that you can use the letters A through F to represent 10 through 15 in hexadecimal. And then with bits, same thing. If you want to define a binary value and a sequence of zeros and ones, you can say 0B to represent a binary literal. How many of you already knew that you could do that? I don't see any hands, so excellent. I added value today. Yeah, so Java supports this, C# I think is the same. Naturally, C++ supports this. So most higher level languages that you're going to use, you'll have these tools available to you should you ever need them. Okay, so we get down to float and double. There's also, so if you're just going to define a fractional literal, it's going to assume that you mean a double in Java. But if you only really want to specify a float, the smaller version of it, the 4-byte version, then you just put the F at the end. So 128.5 float is the way we read that, as opposed to 12,345.67 as a double. So it's going to use 8 bytes to represent scale. Or if you want to be explicit about it, you can also end it with a D, which will allow you to add more digits. If you try to add this many digits and end it with an F, obviously the compiler's going to complain at you because it says, no, that's too many digits for a float. So just use the D. Okay, any questions about that? I know it's weird, obscure syntax, but you've seen it once, so I can put it on a quiz or a test and my conscience is clear. Okay, so another topic we're going to throw out here, again today is a lot of conceptual stuff, is the notion of scope. And if you think about what a scope is, it lets you narrow down to what you're going to focus your attention on. Okay, so if I'm looking at something through a scope, I'm disregarding everything else. I can see everything that's in view of the scope, the scoped area, and I'm disregarding everything else. I can't see anything else. Okay, so in Java we use curly braces to signify where scope begins and ends. Open curly brace, close curly brace. So if you hear me use those words, that's what I'm referring to. And that's how we say them if we're reading our code. And if you're doing, let's say, an assignment statement or you're printing a variable, you can only reference variables and things, data types and things, if they are currently in scope where that line of code is being written. And if things are global scope, that means everything in the program can see them. If sometimes the things will be file scope, meaning you can see it anywhere inside this .java file. Sometimes it'll be function scope, which means, the open curly brace and the closed curly brace that define the start and end of the function. You can reference that variable or that object inside that function. It might even be narrower, like if you're writing a for loop, while loop or something, and that has curly braces, and you define a variable inside that while loop or for loop, then the scope of that variable is in there, and you can't refer to it before or after that while loop because it's out of scope. And the compiler uses those hints, again, to be able to tailor and optimize the code. So for example, if you declare a 8-byte double variable inside a while loop, then as soon as execution reaches the closed curly brace of that while loop and continues on, the compiler knows, okay, you must be done with those 8 bytes, and I can reclaim them. I can go use them for something else. So that's why scope matters, is to let the compiler manage the state of the stack, where local variables and things are stored, and the heap, where memory managed objects and variables are managed, and make your code, because it'd just be inefficient to try to scan your entire program and come up with a list of every variable that you were going to possibly need and allocate them at the beginning of the program execution so that they're there for the 3 lines of code inside your while loop. It would just be inefficient. And in some cases, when you're talking about arrays and collections and things, it just would not be appropriate to do that at all, because you don't know that the number can grow and shrink. So, so this is how it works. We can modify and abuse the term scope further, because inside a class, which we'll talk about when we get there, inside a class you can modify the scope further to say, even if you're inside the class, whether private values and public values and protected values, those modify the scope even further and in different ways. But like I said, I want to kind of kick that down the road and talk about access modifiers when we get to classes and objects soon. Okay, so here's a nifty little example I threw out there. Not a lot going on here. So I've got a class. I define a public, a protected, and a private, 3 integers, right? Pears, apples, bananas. I initialize them all to 0. I have my main function. So when I say Java hello world, and I run this program, it's going to call this main function at startup and immediately start executing these lines of code. So it comes in here and says int peaches equals 0. Well, this is a 4th new variable, another integer. So I declare it and initialize it in here. And as you guessed, the scope of this variable is not the same as the scope of these variables. So inside here, I can refer to that variable until I get down here to this closed curly brace. So this is what we would call a variable with function level scope. Inside this main function, I can access the peaches variable, but not outside it. So if down here in the 2 integer function, I tried to say peaches equals peaches plus 1, something like that, it would say, what are you talking about? I don't know what peaches is. That's an undeclared identifier, or it's a symbol that I know nothing about. I don't know what you're talking about, because it's out of scope. For all intents and purposes, it doesn't exist if you're down here in some other scope. And I feel like I'm beating this to death a little bit. I think you get the point. And the key concept here is just to realize that where you declare your variable, where you instantiate an object, matters to its scope, and you can't just universally create a variable and refer to it anywhere. You have to pay attention to the scope of that symbol and where it's legal to refer to it. Okay, any questions before we get into operators? Okay. So for operators, these are the things that we call them that because they operate on data. And if you've ever had a math class, which I'm assuming everybody in here has, then you're already familiar with most of these, or many of them. And if you've had COP 1000 or equivalent before, you've probably already been introduced to the Python version of some of these operators. So it's another thing, any language that you learn, it's like learning the verbs and the nouns of Spanish if you go try to learn that. When we're trying to learn Java, we're going to have to be familiar with and remember the list of operators that are legal to use in this language, and the context where they're okay to use, and the idiosyncrasies between using them here versus in other languages. It's not necessarily the same as what you learned in Python, but there's probably a lot of similarities. So we got the arithmetic simple set, plus, minus, times, divide. Percent, you remember what the percent operator is? Modulus, yeah. So it throws away the divisor and only cares about the remainder, right? And then the plus plus and the minus minus are nice. They're just shorthand. We have a lot of, in these programming languages, we have a lot of things that are just shorthand for the regular way of doing it. So if I wanted to say x equals x plus 1, which we do a lot of programming involves incrementing a value from what it has to that value plus 1. We do it so often that they came up with a shorthand version of it, plus plus. And that was an innovation, I think, that came around with C++, and that's the reason why they called the C++ language C++, is because it had the plus plus operator. C doesn't have the plus plus operator, but C++ does. And then likewise the minus minus to decrement a variable. So we would call that the increment and decrement operators. We throw those under the arithmetic because they essentially do the same thing. As x plus plus is the exact same thing as x equals x plus 1. Then we get the comparison, and the thing that calls out the comparison operators is the fact that these are all asking a question. So instead of saying, when we use the, down here at the bottom, the equals, I just kind of glossed over x equals x plus 1. The way you read that in humanese is to say, set x to x plus 1, right? Assign x the value x plus 1 is how we would say that to each other. But with these comparison operators, even though it's equals equals, we don't say the same thing. We say, is what's on the left equal to what's on the right, right? So if it's x equals equals y, we're saying, is x equal to y? And so when I'm reading my code, I try to tell myself in my head so that I don't get those right. There's been innumerable logical errors introduced into programs because people typing equals instead of equals equals and getting those confused. So whatever you can do to train your mind to think of it in terms of, no, they're completely different things. Equals is assign this variable to this value, and equals equals is this equal to that? So that's how you read that. But that's common to all of these comparison operators. They're all asking, compare what's on the left to what's on the right, and return true or false. So these comparison operators all return a Boolean value, logically Boolean. It's only either true or it's false. So if you're looking at an operator that returns true or false, it's a comparison operator. Same with logical, but we're doing, you could call these logical operators comparison operators, well, except for the not. But the and the or, you could call those comparison operators. They just happen to be operating on Boolean values. So not only do they return a Boolean result, they operate on Boolean values to start with, whereas the comparison operators often are working on numeric operators, float or number. A little known fact that we don't mention, I'll just throw this one out there as bonus. When we're doing a for loop, usually and we'll talk about that when we get to the repetition, but it has to do with comparison. We usually use integer data types for loops because they always stop on a whole number. But you should not, it's incorrect to use a float or a double to control a for loop, because in really weird scenarios, you get to a point where you hit the end of what should be the end of your loop, but the floating point comparison No, there's this fractional value out there that makes it not quite true yet, or not quite false yet, and so it loops one more time than it should have. And so that's just a weird little fact with these comparison operators and float values, float and double. So file that away under miscellaneous. Bitwise, this confuses a lot of people. What's the difference between ampersand and double ampersand? Or the way I read it earlier, and versus and. That's the way you'll commonly hear people refer to these. The bitwise and, what's on the left and the right, you're going to consider those as a collection of bits, and you're going to process them accordingly, bit by bit, not numerically, or not just as true false. So I could have all kinds of fun giving you assignments and things where I drill that into you, but for now we'll leave it there. And same with the single vertical bar, it's or versus or. The logical one always have two, and the bitwise always have a single. The little caret here is what we use instead of the exclamation point for the not. So, the not also works on bits. It just reverses them from a 0 to a 1, bit by bit. And then the tilde is, anybody know what that is? Have you come across that before? Bitwise operator tilde? Nobody? Oh, man, I'm providing so much value today. So this is what we would call the exclusive OR operator. It works on bits, and you can look up the truth table for exclusive OR, but if I have a 0 and a 0, no, they're the same. So that would actually be true or false, yeah. Or, because it's or. It says basically one or the other of the two can be one, but not both, and not neither. Okay, so that's the definition. You've heard it. It's on the recording for posterity, but look up those if you're not convinced or if that's confusing, and see what the difference between or and exclusive or is. And then we've got a whole bunch of these assignment operators. The equals is the basic assignment operator, and all the rest of these are shorthand. They're shorthand for what's up above. But, the plus equals says basically add a value to a variable. Minus equals is subtract this value from the variable. So instead of x equals x plus 5, you can say x plus equals 5. It's just shorthand for all those. You could work your whole career and never even care about any of these assignment operators except for the equals. Except for the fact that if you ever have to read code that somebody else wrote and you run across any of these, you just kind of need to know what they are. And once you know what they are, eventually you'll just get to be, why do I have to type the variable name twice? I'm just going to start using these assignment operators. Because we're lazy. And saving one character or two characters after the end of the day, when this is what you do for a living, if your job is to put 50-pound bags of cement on your shoulder and carry them from the truck to the job site, and somebody points out to you a more efficient way to do it where it's less work, well, that saves you quite a bit of work after the end of an 8-hour day. And it's the same thing. If you figure out some of these little shorthand tricks, if you're sitting there at your keyboard typing code, Java code, for 8 hours, then these little tricks will start to help. Okay, next in line is expressions. So expressions are essentially combinations of all the things that we've been talking about before. Variables, literals, operators, assignment. Combining those things together is what forms expressions. And so, this is nothing that you haven't seen before. You would have had all of this in COP 1000, so hopefully it's review. But the key thing to remember is as you're reading your code, You know, when we see an equals, an assignment operator, you always remember we evaluate what's on the right side of the operator first. We have to come up with what the value is before we can assign it to the variable on the left side of the operator, of the assignment operator. And likewise, the order of operation inside the expression is how we evaluate it. I think I've mentioned that last time, that, you know, they've got those little memes that talk about, you know, what's the value of this expression, hint, it's not 17 kind of stuff, where they're trying to trick you by making you try to figure out what order that they're doing the math and seeing if you know how to do it. So here's a little bit of code. So I declare a variable called computed value equals, so I've got an assignment statement or assignment operator. So I want to evaluate what's on the right side first. 9 times O. So I've got parentheses. Has anybody ever heard that acronym PEMDAS? P-E-M-D-A-S? Right, PEMDAS. If you can remember that, that's supposed to be a way to remember the order of operations. Parentheses first. What comes next?
Exponent.
What?
Exponent.
Exponents.
And then multiply.
Then multiply.
Division. What those are.
Then addition.
Subtraction.
And I put these on the same line because essentially we always go left to right by convention with the multiplication and division. So if you see 5 times 4 divided by 9 times 2, then, you know, there's a little bit of concern. Wait, is it 5 times 4 divided by 9 times 2? Or is it 5 times 4 divided by 9 times 2? And since there are no parentheses, we would just do this from left to right. We do 5 times 4 is 20. 20 divided by 9 is whatever that is. And that times 2. And that's how we would evaluate that expression, right? Left to right, because there's no parentheses. And yes, obviously, if I had parentheses around that, then I would do that first, right? Okay, you guys get it, right? But just remember that PEMDAS, if you forget. Of course, it doesn't always help me because I always forget what the E is. What the heck is E? Oh, yeah, it's exponent. You always do the exponents first. Okay? All right, so 9 times, got parentheses, so I do the 5 plus 3 first, 8. 9 times 8 is 72, minus 12, so that would be 60. So computed value is what would get the value of 60. I evaluate the expression, and I assign it to the variable on the left. Everybody got that? You agree that it's 60? Not just because I said it was, but because you understand how it was evaluated. Parentheses first, there's no exponents, multiplication, division, and then addition. Okay, the next one. Okay. So PEMDAS is more of a Python thing. In Java, we have more operators. So we've got this greater than, So I didn't really talk about what any of those greater than, less than operators meant. But anybody know what they are? I gave you a hint by saying it's a 0B.
Memory offset?
Good guess. It's a bitwise shift operator. It says take the bits in this and shift them to the right one. Well, what happens if I take the value just a one single bit, and I shift it to the right one value. I'm not sure I thought through this expression. I think I was probably just typing a bunch of random stuff up there. But if I shift a 1 to the right, it gets rid of the 1 and makes it a 0. What I probably meant to do is say less than, which would have shifted it to the left. And here's a cool little trick in binary, is anytime you take a collection of bits and then you shift the whole thing 1 to the left and put a new 0 on the right, you essentially have multiplied it by 2. So that's shifting the bits to the left one place is essentially the same as multiplying by 2. And hint, that's how the CPU does it, actually. If you say multiply it times 2, it's going to shift all the bits over. Likewise, shifting them to the right divides it by 2, but it also loses the remainder. So in this case, we would take 1 bit and shift it to the right, dividing 1 by 2, which we get a half. We throw away the remainder and we're left with 0. So 0, and since it's bitwise, we do that first in the PEMDAS. So parentheses, then bitwise, then exponents, or bitwise and exponent may be the same level, but I think bitwise is first. You might look that up and check me on that. So I basically get 0 times computed value, which we said was 60, but it's irrelevant now because we're going to get 0 because we're multiplying 60 times 0, plus, then we do the 12 divided by 3 before we do the addition, so that comes out to be 4. And so, and another gets set to the value of 4. So it takes a little bit of thinking about it, but once you get good at this, then you can kind of do all the arithmetic in your head. And one big point I will make to us as programmers, as professionals, is don't leave it for somebody else to guess. Don't make people remember the order of precedence. If you're doing it this way and you're doing it this way on purpose, put the parentheses in there, even if they're not necessary, because it's self-documenting. If you really intended for this operation to be done in this order, use the parentheses. Help a brother out. It's not that much more typing to be clear about what you're doing there. Because just reading this, I would have no idea what we were trying to calculate here. Is it the number of pears on the trees in an orchard? I don't know. So a little bit of comments and some parentheses would greatly help this. But back to the point, you get what we're talking about here is you have to understand the operator precedence rules and calculate these things in a particular sequence. Otherwise, you're not going to get the value you intended, or you're not going to understand what value is being assigned there. Okay, so next we're going to do the math class for a moment. So inside the math object, it's probably easier to call it object than to class because it's kind of ambiguous with being at school. But the math object has a whole bunch of useful stuff in it, and you can, Google the Java math class if you want to see the full list. I think on Oracle's site or, W3 Schools or some places like that, they're probably good reference lists of all of the things that are defined inside that object. But the usual suspects, sine, cosine, tangent, logarithms, square roots, all the kind of useful formulas that you would never want to have to write yourself. The other group of them are the minimum and maximum. If you have a couple of values and you want to say, well, I really want to just know which one of these variables has the minimum value. One's got 7 and one's got 12, and I don't care. I just want to know whichever one of the two values is the lower one. Then you use the min function. That way you don't have, it's just shorthand for saying, if x is greater than y, then pick y, else pick x. You could write that yourself, but it takes 4 lines of code instead of just saying the min. So that's why we use that. And then random numbers are fun. We'll probably do some stuff with the random number generator. And typically the way random number generators work, there's a couple of different ways. Like in C++, you get a random number between 0 and 1, I think, and then you multiply it times the range of values. So if you wanted a number between 0 and 100, 0 through 99, then you would say, give me a random number and multiply that times 100. And then you would read that and know, oh, well, that's going to give me values from 0 to 99. But in Java, I believe the way it works is you give it parameters. You give it the low value and the high value. And check me on this, but best of my recollection here standing in front of the camera is that if you give it 7 and 12, you'll never get 12. You'll get 7 through 11. 7 up to 12, but not including 12. But check me on that. It's really important to know that, because if you're trying to precisely get a spread of values back from the random number generator, you want to know what the min and the max values that you could possibly get are. I've had many times where I didn't quite understand or didn't remember what the rules were for that particular language or that particular object, and I was getting random numbers back that either were out of range or I was never getting the last one that I expected to get, and it can kind of mess up your results if you do it that way. It never hurts, if you haven't used one of these functions in a while and you're about to just, I would say hit the F1 key or go to Google and look up the Java random function, Java math.random, and just read a couple of line description of it so that you refresh your memory on how it works. And that falls into the category of, I've said this several times, but I try not to memorize this stuff anymore. I just know several ways that it typically works in different languages, and then if I need to remember which way it was, I go look it up, because you can never memorize it all. Every now and then you'll get some guy in a job interview and it's like, oh, he didn't remember exactly how the random number function worked. And I would say back to the person, why would I waste brain cells on that? It's so arbitrary to have to remember that. Why can't I just hit the F1 key or Google it? But, your mileage may vary. Okay, next topic. Any questions there about that? I know I'm running through these things kind of fast because I don't want to make this longer than it has to be, but we'll get through it. Okay, talking about conversions. We have what we call implicit conversions. So if I say long value equals 1, that line of code is going to take the value 1 and assign it to the location reserved for the variable value. And the value is of data type long, and so we know it's going to occupy how many bytes? 8. Yeah, int is 4, long is 8, right? So I'm going to have 8 bytes, 64 zeros and ones, but the only one that I'm going to actually be using is the bottom one. And I'm going to set it to a 1. It's going to be all zeros, and then that last bit is going to be a 1. So when I do an assignment statement like that, it doesn't require the compiler to do anything special. However, whether the compiler creates a 32-bit value and sets it to a 1 and assigns that to the 8-byte value, I don't know and I don't care, as long as what I get is an 8-byte variable called value that has the value 1 in it after this. I don't care. But the point is, there's no data loss possible doing that on assignment, so it's an implicit conversion from the literal 1 into the variable value. Likewise, if I'm going the direction of a smaller or the same size data to a bigger one, if I'm emptying a smaller bucket into a bigger bucket, there's no conversion required, there's no data loss possible, so you never have to do anything special. It's always an implicit conversion from one to the other. okay? So a byte can fit into a short can fit into an int can fit into a long, et cetera, et cetera, et cetera. But if I'm going the other direction, if I'm assigning a bigger bucket and I'm pouring it into a smaller bucket, I could possibly have some data loss there. I could lose precision, is what we would call that. And so the compiler wants to make sure that you're doing that on purpose, that you realize that some data loss could occur. I'll use the boat analogy yesterday. Before he checked the software on my chart plotter to see if it needed to be updated, he was really nice and he asked me, by the way, do you have any settings or waypoints on your chart plotter that you don't want to lose? I said, obviously yes. I don't want to forget the little path through the narrow shoals and the coral reefs and all that I took to get to where I dropped my anchor. I have that on a little purple line on my chart plotter and I don't want to forget that. So thankfully he backed it up, did the software update, and then restored the settings so that no data loss would occur. So thank you for explicitly asking me if I wanted to lose my data. Otherwise I would have lost my data accidentally. So the compiler is similar. It says, you can do that. I'll put the bigger bucket into the smaller bucket. You just need to typecast it and tell me that that's intentional. So all you have to do is say, value is an 8-byte piece of memory, but I'm going to put short on the front of it because I want the compiler to truncate everything but the last 2 bytes and only copy those 2 bytes worth of zeros and ones over into small value. You're just explicitly, you get it? Implicit before, I didn't have to say anything, it was implicit, the conversion required. Now I have to be explicit. So it requires an explicit typecasting or conversion to put something bigger into something smaller. It'll do it just fine. It just wants you to tell it explicitly that you meant to do that. And there's some non-obvious cases here that you'll run into and you'll wonder, why am I getting that silly warning from the compiler? If you say small value divided by value, that's think about this, it's a 2-byte number being divided by an 8-byte number in this example. So what's the result going to be? How many bytes is the result of that going to be? We'd have to look up the divide operator. And the divide operator says it takes an integer on the left and an integer on the right, I believe. So the result is going to be an integer. So if I want something else, I need to be explicit. Other compilers, they work left to right. So it might say small value is a 2-byte number and you're dividing by an 8-byte number, so the result is going to be a 2-byte value. And then obviously that is going to cause an issue, because if I'm dividing a 2-byte value by an 8-byte value, there could be some data loss, shoving the result of that back into a 2-byte value. So I might have to put double on the front of it, like the second example here, to explicitly tell the compiler, yeah, I know that could happen, but in my case, logically, that won't happen, or it'll happen and I'm okay with it. So yes, explicitly go ahead and do that. Does that make sense? Yeah, because if I'm dividing this by that and they're both floating point and I'm getting an integer back, it's not going to keep any of the fraction. That's a very common thing. Well, I divided 2 divided by 5. Why did I only get 2 as my result? Why didn't I get 2.5? It's because it was an integer expression. It calculated 2.5, but then it shoved it into an integer, which lost the 0.5. So all you got back is a 2. And you're like, well, that's confusing because the left side of the equal sign is a double. It's got 8 bytes of decimal fractional data that it can store, why did I only get 2.0 as a result? And it's because you have to account for the fact that that divide operator only works on integer data. Okay? Everybody understand that? Yeah, it's one of those things where it'll float around in the back of your head, and one of these days you'll be getting some weird results, and you'll step through it and say, wait, why did I get 2 instead of 2.5? And you'll remember, oh yeah, Dr. Snyder said something about that. What did he say? And then you'll look it up and realize, oh yeah, I should have remembered that. It happens. Wait till you get my age and you don't even remember it. Okay, next, set the numeric stuff aside and we'll go do some stuff about character data real quick. We're getting close to the end. I think we've got 3 or 4 more slides left, so bear with me a little bit longer. So we've got this System.out class, and that's what we use, you know, in Python. It's just print. The print statement is global, so we didn't have to mess with this. But in Java, they organize all of the methods that we have available, all the functions we have available. They organize them into object hierarchies. So the print and print line methods are part of the System.out class. So we just have to know that. So you would just say System.out.print in order to print to the console in Java. Likewise with reading user input, you'll have to read, you know, it's different than just using the input statement in Python. You have to learn about input streams. But one convenient thing to do when we don't want to get into all that is that the java.exe will take all the parameters that you give it on the command line, and it will parse them and populate them into this args collection, and so that you can access them easily when your program runs. So that's very convenient that it does that for us, so that we don't then have to get into a whole bunch of input stream stuff if we don't want to at the start. You can just expect all your input to come in on the command line, and it makes it a little easier initially, a little bit more approachable. So we don't really add and subtract strings, right? We'd have to convert them to a number and then do the math. But when we do operations with strings, we talk about concatenation, which is taking 2 collections of character data and making them one collection where one is the suffix and one is the prefix and one is the suffix. So that's called concatenation. Just put the 2 strings together to produce a new string. And it's important to realize that that's how it happens. String handling is traditionally very inefficient. If I have a string that contains the word dog and a string that contains the word cat, and I concatenate them together, now I have 3 strings. One that contains dog, one that contains cat, and one that contains dog cat. Right? So you can end up churning through quite a bit of memory pretty easily and not realize it when you're dealing with string handling functions. When you're parsing or you're splitting on characters and things, you can end up exploding into a whole bunch of individual objects. Now, we typically don't care because it's fast enough that you know, we don't notice as fast as these CPUs are nowadays, but it still bears considering that you know, to avoid string handling operations unless you need them. When you need them, you know you need them and do them because that's what they're there for, but don't just do them willy-nilly. Like we wouldn't want to write a program where we store all of our numeric data in strings and then convert them to integers to do the operation and then store them back in a string, because that would be incredibly wasteful with all that converting back and forth and parsing and stuff. So yeah, we wouldn't do that. And then yeah, so splitting is taking one, you know, you'll see splitting a lot. There's a split command where if you have a sentence of words and you know that there's a space in between each word, you can say, hey, here's a space character, split this big string of characters using the space as a delimiter. And then you'll get back an array of individual strings. So again, we're going from one big string to one big string and a whole bunch of little strings. So we've doubled the amount of memory we're using by doing a split operation. Regular expressions are something also that we can do. My voice is starting to go, so I'm not going to go deep into that. But regular expressions are there to help recognize patterns of strings. Like if you have somebody, please enter your street address, you can create a regular expression that says, okay, it's going to start with 1 to 5 numeric digits, then a space, then some characters, and then a comma. And, you can lay out the pattern for your string, and then use these regular expression operators to say, based on that pattern, split the big string into substrings where each of the substrings matches one of the pattern specifiers that I put in the regular expression. It's very helpful, very powerful, very easy to have subtle issues and completely screw it up. If you've ever gone to somebody's website and it says, please enter your street address, and that says, oh, I'm sorry, that's not a valid street address because you have a P.O. box or a pound sign or somewhere in there, and it's like, that's my address. The post office knows that's my address. Why doesn't this website recognize it? Well, it's because some programmer did the regular expression wrong, and it doesn't recognize it as a valid pattern that they're going to accept. That's what happens there when you have subtle regular expression issues. But they're very powerful, very useful if you spend the time and invest the time understanding how to use them and how they work. They can save you a lot of code and a lot of time. Typically in computer science, the alternative to regular expressions is to write a whole bunch of lines of code as what we call a state engine, a state transition engine. That's what you typically would use for parsing. And if you take, higher level computer science classes, you probably have to build some state engines. And then there's a bunch of functions that operate on strings, and typically we're talking about, hey, I've got this string, how many characters long is it? What's the length of it? So you can get the length of the string easily by just calling a function and passing that to the function. You can trim so many characters on the left, you can trim so many characters on the right. You can get a string inside the middle of it, but it gives you really powerful ways to manipulate it with all these string functions. And I would just recommend you look up the string class and look through the list of all the methods available to you in the string class, and you'll eventually use most of it, if not all of them. So it's good to be familiar with them and know that they exist. Another thing when we're producing text output on the console is to understand the carriage return, line feed, and tab characters, \r, \n, and \t, because it's really nice and it can make your output kind of pop to be able to format it intentionally. And then we have other string functions that can like take a number, and if you want to print a bunch of numbers and have them all line up on the decimal point, there's ways that we can format our string output to get that to happen. So you have to learn all those print functions. We had some of that in Python, so if you remember that, the F strings in Python that you had to learn. This will be similar to that. We don't call them F strings, but they're string format specifiers in Java that we use in conjunction with the print and the print line methods to format our output the way we want it to look. Yeah, lots of cool stuff, but I'll move on. So when we talk about conversion with character data, similar to the way we talked about conversion with number data, it's a lot simpler. Usually what we're wanting to do if we're talking about conversion with character data is that we've got the user entered a string on the console that we want to convert from character data to a number, like we said, enter the number of peaches, and they enter 27, and we want to take that 27 as character data and convert it to an integer, then we would say integer.parseInt. That's the method that we use. And each one of the numeric classes will have a parse method, one or more parse methods, and you just have to look those up and see how they, but you know, they all follow a similar pattern. You pass them the string, and if possible, they will convert that string into that data type for you. There's a whole bunch of other, like I said at the beginning, there's a whole bunch of other types of objects, classes of objects that we can get into, and you know, we'll continue to expand our experience and our knowledge about those as we go. But there's a few of them, you know, around collections of data, and then as we build our own, you know, like customer or user object or animal object and things like that as we go. Then we'll start, when we get into classes, we'll start looking at the different idiosyncrasies of that. And that's pretty much everything I wanted to introduce today. Anybody have any questions about what we've talked about so far? Okay, hopefully that, yeah, go ahead.
The final, when it was like final double, is that the same thing as writing constant and then dividing the variable and then?
Yes.
Okay.
That's all it is. Creating some symbol for a value that you want to stay the same for your whole program. Yeah. So hopefully that complements what you're also reading in the textbook fairly closely. Hopefully I haven't contradicted the author of the textbook too much. If so, he's probably right, and I'm just not remembering it. So keep that in mind. Okay.